Greetings, everybody. Welcome to the Evidence and Reasons video channel. I'm really privileged this evening to be joined by Dr. James Carter, who's a professor of various topics in chemistry, and he is a professional biochemist. So today's topic is racemization dating and also maybe other chemical clocks. This is going to be kind of technical, but he, in the topic that when Dr. Rob Stadler gave his presentation on the Standing for Truth channel, I was just thrilled to hear that Dr. Carter had actually done some work on this 12 years ago. No, maybe 15 years ago also I'd been doing this, and it sparked my interest in chemistry and biochemistry. At the time, I didn't even have my master's in physics. I didn't have any biology training. So in the 15 years intervening, this interest in creation science has sparked my study of science. So when people say that creationism kills science, that's definitely not the case in my life. It sparked more interest in my life for science and to become a good student. I was actually a pretty lousy student getting through school. And so without further ado, Dr. Carter, can you introduce a little bit about yourself for those of us who might be new to your background?
Yeah, I am fairly new to the YouTube community. I've been listening to Sal's channel and a couple of other creation evolution channels since about the summer. Something I've been interested in since high school biology, probably my first science class. And ever since then, I've been in a lot of science classes. I had 27 years of school, and more than half of that was science classes. And then I've created 15 different science courses, mainly biochemistry related, because that's what my PhD is in. And but I've been so busy for the last decade, I've gotten kind of behind on what some of the latest findings and arguments are. So I've been playing catch up, a lot of it by watching channels like Sal's, and he mentioned amino acid racemization, there's two different ways to say it. And I thought, well, yeah, when I was in graduate school, during some downtime, we had to have these advanced topics courses, but they're only offered every couple of years. And I thought, well, why don't I write some papers and get a professor to be my mentor or teacher for that paper and get a grade on it? So I kind of killed two birds with one stone. I got to fulfill a passion of mine by looking at some of the scientific evidence that supports the testable claims of the Bible, and I got course credit for it as well. So I wrote two papers. One is on ancient biomolecules, and I got through about maybe 150 or so references and reviewed them and wrote up the results of that, showing how as a biochemist who works with protein and DNA a lot, I know how fragile these molecules are. Yet they're being found all throughout the fossil record. And I thought, well, something's not right here. Either these samples are contaminants, which was the argument made by a lot of molecular biologists and biochemists like myself, that this is just impossible for them to be around for millions of years. Or there's some unexplained chemistry that goes beyond anything we're familiar with that can somehow preserve these molecules. And the third option is maybe they're both right. Maybe the paleontologists are showing, and they have done so in hundreds of papers now, that this material is authentic. It's original material. It's found throughout the geologic column and in partially fossilized remains. And of course, I have to side with the biochemists as well that say all the forensic studies, all the empirical evidence we have shows that these are short-lived, labile, unstable molecules. And we're familiar with the instability of things, even when kept cool and dry. The medicines in your medicine cabinet have expiration dates after a few years because they start to degrade and they won't do their job. Sometimes they can even degrade into toxic compounds. But usually they just lose their effectiveness. And these are mainly organic, pretty stable molecules. What about biological molecules? even your water bottle has an expiration date on it. Not because H2O expires, but the bottle that plastic bottle that's so difficult on the environment and can take, more than 100 years to start to break down. It's breaking down, just sitting there. If you've ever left a water bottle in your car too long and then you drank from it, you can really taste the plasticky chemical taste as the molecules start breaking down.
Oh, is that the reason? Well, I learned something today.
Yeah, it's leaching stuff into your water, small molecules. So it will eventually degrade just like everything else. All things go to what I call molecular entropy, as an homage to Dr. John Sanford, your mentor, his genetic entropy. I think not only are our genomes degrading, but also the molecules have high degradation rates, and they simply shouldn't be there in the fossil record. So one of the things we're going to look at is proteins in the fossil record, and whether they have undergone a type of degradation that we can measure in the lab called racemization.
Well, I think I'm going to defer to you for how you'd like to have this talk. Maybe I'll just share a few things. For myself, I was an old Earth creationist up until about 2000, 2001. After I became a Christian in 1978, I probably still believed in evolution for about a year and a half. But then when I learned about the problems with abiogenesis, I rejected it, because if you can admit one miracle, you can admit so many more. So even though evolution and abiogenesis are not the same thing, just the complexity. And I didn't really know very much, but it was an adequate argument. And because I'd been fascinated with physics and astronomy, I had accepted the mainstream view. And I still think that there are a lot of challenges for the young creationist view for the Earth or the cosmos. And I know that there are a variety of views. There are views where the universe is old, but the Earth is young, and we don't need to go there today. But in 2001, I had a little bit more physics and science training at that point. And I began to read, and I said, there's some serious problems at every level. I said, maybe we need to do a timeout. And I just began to look at the data, and I began to say, I can't believe the mainstream is so convinced, because there's at least these anomalous data points. And then in 2004, 2005 timeframe, I began to look at the question of racemization, and I said, this is actually something I somewhat can understand, even though I had only general chemistry courses up until that point. I said, I totally understand the idea of what you called molecular entropy. And just to clarify, I would presume this relates to the entropy in the Gibbs free energy. Is that because I see it in the equations? I actually saw an equation for racemization. What is the change in Gibbs free energy? And they actually give the figures. So I looked that up in stereochemistry and optical chemistry. So I began to look at it, and there was some invariance. There was insufficient variability from across the strata. I said, this is really, really problematic, and there shouldn't be any they gave up at 10 million years, but I think I saw one paper by Jeffrey Botta that was saying that there was unracemized amino acids in the Silurian. That's like, I would guess, hundreds of millions of years, and they just attributed it to contamination or something else. And it was the works of Michael Brown and R.H. Brown at Loma Linda, GRI. And I said, oh my goodness, this is really powerful. And I ran it by some of my most hostile critics, and they had no counter. And even at that time, I wasn't really, and I was kind of halfway between old Earth and young fossil record. And then, but that never changed. And then when I went to graduate school in physics and I studied cosmology and astrophysics, I said, oh my goodness, I think anything can be on the table at this point, because some of their explanations to resolve the anomalies are no less outrageous than assuming anything in any of the variety of young creation models. and that changed my views. And then now more recently, when they start invoking multiverses to explain the origin of life in the universe, I said, okay, anything's game at this point. So even wherever anyone might be in their personal beliefs, we could explore this from a purely scientific question. How could it be in that state? So I do have the papers here by Michael Brown and R.H. Brown, and you can also share your screen if you wanted to just share anything that's on your heart.
Before we get started, we should probably explain to the audience who haven't taken a chemistry class
Yes.
what racemization is and what are the amino acid, what does D and L mean?
Yes. Yes.
Are you going to cover that in your portion of the talk?
Well, I'll tell you what. Maybe you can help me through the graphs. I have the papers by Michael Brown here, and maybe I can page through it, and maybe you can.
I got it. I went ahead and built a few. I happen to have one of these chemistry model sets to try to help explain some things that might help a non-chemist understand before we get going. But
see if I'm going to try to get you to have the best. I'm having a hard time getting the view where you can get the maximized.
Oh, maybe I need to do it.
I don't know if I can.
Nope.
There has to be a way I can give you the. I haven't figured out how to do that in StreamYard. So let me see if I can. It's always making me, because I guess I'm the host. It makes me the primary, and I really want to make it.
I'll try to hold them up close, so maybe
okay,
people can see easier. So what we're talking about with racemization is molecules can exist in three-dimensional space, which isn't always easy to draw on a piece of paper, which is only two-dimensional. So we like to use these little chemistry models. I'm sure you've seen them, which even this is not a good approximation of what the actual molecules look like, because the atoms aren't, hard spheres like this, and they don't have tough bonds like you see here. These just represent a covalent bond. That means that the electrons from this atom and this atom are close enough to each other that they end up sharing. Neither one of them has as much electrons as they would like, so they partner up, and share their valence electrons. So covalent sharing of electrons here to form a bond. So this is not a rigid thing. It's somewhat flexible, but it does have this general shape, which we call a tetrahedral shape, with carbon in the middle, that black atom you see there. But you'll notice there's actually a couple different ways we could represent. See if I can line these up so they'll be mirror images of each other, or not mirror images. So here you can see that these are, if I put a mirror in between this and took one away, they would look identical. They're mirror images of each other. And carbon can do this if it's got 4 unique things bound to it. So I just represented that with different colored spheres. Don't worry about what element they might be. So if I want these to look like each other, to be the same molecule, let me pull out here. There we go. This is tricky. I would need to actually say, take the purple one off of here and swap it with this green one. And then I would end up having the reverse of that. But just by twisting this around, I don't get the same molecule. They're actually different. Even though they have the same composition, they're both isomers. They both have the same number and type of atoms. They differ in three-dimensional space. They're not superimposable. I can't just overlap them and you get the same molecule here. So it requires bond breaking and reforming in order for you to get a left-handed and a right-handed structure. Now, why do they call it left-handed and right-handed? Well, that has more to do with how you detect these molecules using plain polarized light, and I don't want to get into that. It bends the light to the right or bends it to the left. So if you have a solution of just one of these isomers, stereoisomers, the light would get bent to the left, and we would call that an L in the L configuration, stands for levorotary. So it means left-handed, basically. It rotates to the left. And they could have used R for right, but it's a, I think it's a Latin term, so it's dextrorotary. I think I'm more dexterous with my right hand because I'm right-handed. So D means the right-handed. So you have a left-handed and a right-handed. And there is a way to determine whether something is left or right-handed. I don't think I need to get into that. But the important thing to remember is in nature, for some reason, the amino acids are all L or left-handed. Most of them. There are some examples where you can find D amino acids in nature, but for proteins, they're almost always in the left-handed configuration. And sugars can also have isomers, stereoisomers, and for whatever reason, they seem to be in the right-handed configuration. Now, no one knows why that is. If there was a primordial soup situation and you could form randomly different sugars and different amino acids, you would get a roughly 50-50 mix of the two. And even if you started off with pure, 100% left-handed amino acids in a solution and 100% right-handed sugars in solution, over time, those bonds break and reform, and eventually you get a roughly half and half mixture of the two. So you would have about 50% D and 50% L amino acids, and same with sugars. And it takes a while to do that. And there's a lot of factors that can determine the speed that happens, especially temperature and pH and the burial environment, how much water is present. So scientists figured out, I guess in the 70s, that you could use this as a sort of dating method called amino acid racemization dating, where if you took an old sample and you looked at its composition of amino acids, you can take the proteins and chop them up into pieces so that you're left with just amino acids that used to be linked together to make the protein. They could analyze and say, well, if it's a fresh protein, it should have almost entirely L amino acids. And over time, after the organism died, time and chaos and chemical reactions start to make some of those L amino acids flip to the D. And some of the D will flip back to L, but mostly you'll reach a point where you started off with almost all L, and then as they go back and forth, flipping to D and L, you get a roughly 50-50 mixture. And they try to do empirical studies in the lab where they take known proteins that are fresh and heat it up to try to accelerate the aging process, and then get a rate at which each of those amino acids will flip from the L to the D configuration. So that's what amino acid racemization dating is. It's using the principle that there's a somewhat of a constant rate at which the original amino acids start to spontaneously convert into the unnatural D isomer. And if you can figure out that rate, you can figure out how old that protein is. So even forensic scientists will use this if they find, say, a tooth from a murder victim. They want to know how long ago did that person die. They can extract the proteins from that tooth, and based on these known racemization rates, they can say it looks like this person died about 62 years ago, plus or minus 5 years, based on the degradation rates. And of course, the most important thing there being that that the burial environment has been consistent. So that tooth hasn't been transported, the temperature hasn't changed. If it's right on the surface of the ground, of course, it's getting hot in the summer and cold in the winter, and that's going to throw everything off. How much water is running through that skeleton? What's the pH of the soil? Did it ever change? There's many factors that can influence that rate, and you end up with dates that are really confusing or just aren't accurate. Oh, Matt, Sal, you're muted.
I keep doing that. That's just we're near a fire station, and we just.
I do it all the time. Yeah.
Yeah.
I've been teaching on Zoom for like more than a year, and I still sometimes forget to unmute myself.
Oh, I still do that. If it weren't for the people in the chat or my co-hosts, I'd be giving entire lectures and I'd be muted. So um, I wanted to just interject. Even if we're not able to determine the exact date, my understanding is that even if we give the most generous parameters, some of these things should not be, they could not survive hundreds of millions of years. That would just be, from everything I understand, even if you gave the most, like, say, temperature, if you have a very low temperature, like, say, freezing, which would probably not be very conducive to certain life forms, but just assume it's freezing temperature, even slightly below. When I was putting these parameters in, with what little I knew, I said, I can't justify that some of these fossils are hundreds of millions of years old. So even if we can't affix the exact date, we could say it's not other dates for sure. Is that fair?
Yes, absolutely. So that's really the take-home message of this is, one is you can't really rely on amino acid racemization dating if you don't know the burial history. And of course, for some of these paleo samples, we can't really know with certainty. I mean, there's other tests you can do to get an idea of what the environment might be like. So it's not really reliable for getting accurate dates beyond what is historically known or what you can confirm with other methods. But in the same sense, we can also say that there is a maximum at which, no matter how good the preservation conditions are, if it's cold, very dry, I mean, even in amber, like insects and things trapped in amber, which is, of course, really dry and the proteins don't have any place to go. It excludes a lot of the, contaminants and enzymes and things that could mess with the dates. You still have some racemization. It's much slower, but there is a limit, where you would not expect to pull up like a T-Rex fossil with soft tissue inside of it and still expect to see quite a bit of the L-amino acids intact if it was 65 million years old. So you can use that excluding the possibility of contamination with recent contaminants. If you were careful to isolate the protein and then separate the protein into individual amino acids and then analyze those amino acids and see that there's still quite a big proportion of them that are still in the L configuration compared to the D, that would indicate that these things can't be that old. I mean, this is what the testable prediction here is that, from a young Earth creationist perspective, we predict that there would still be plenty of, the ratio of L to D would still be pretty high because not enough time has gone by to completely racemize them, or the racemization process has to have some explanation of why it would be halted to the point of becoming just a trickle compared to the known rates that we see when we use modern samples and do extrapolation experiments.
Yes, and I wanted to just say that people have criticized me for having a young fossil record view, and I'm just like, well, I've heard some of these debates, and I'll say, well, the other side has some points, but I'm just like, I still wouldn't want to be arguing their side. I mean, yeah, I wouldn't want to be defending their side because we have these anomalies like this. I'm just like, at the very least, their side should be saying, well, we haven't resolved all these problems, and they're just glossing it over. And I find that really disturbing. And it's getting so bad. And I wish I had some of the papers, they're actually suggesting alternative chemistries to explain, because it doesn't agree with any of our chemical kinetic models. The only reason I'm showing this graph here, I did promise it in the video description that I'd cover the Arrhenius equation. This is the effect, this T here in this equation, as the temperature goes down, it will affect the rate. And we can slow down the rate of racemization by decreasing the temperature. And conversely, as we increase the temperature, the rate increases. Now, I'm just going to unshare that. I just wanted to kind of cross the T and dot the I here, since I invited people to base partly on that. And when I put these parameters in, I said, well, you're going to have to freeze the oceans at least to slow. You're going to have to freeze all the oceans and keep them frozen. And I said, that's just not going to work if you want to just invoke temperature. And so now they're kind of in a position they're having to try to, I saw some papers said, there must be new chemical kinetic theories here, because obviously these fossils are old. And I wanted to say, well, there's one alternative you guys are definitely not considering. Now, the other thing that I'm just throwing this on the table, it's nothing that we were going to resolve today, is Dr. Jay Wile, who is analyzing some of the discussions on, what did you call it? Ancient biomolecules? There was a certain term, what was the term?
Paleomolecules, ancient biomolecules, yeah, just these
Paleo, I like that.
Proteins, carbohydrates, DNA, and lipids that you find unfossilized in the geologic column.
So these paleo biomolecules, Jay Wile said, and I'm embarrassed to say this, I haven't had organic chemistry. I've had several biochemistry, and it's always bit me that I haven't had the organic, and I'm going to go back. Now, I took my biochemistry at the NIH, and there are a lot of people there that are not biologists. They're computational scientists, and their skills are extremely important. And they're physicists and mathematicians, and they need to get some training. And it's like, okay, we'll retrain you. We'll give you the basics. So the professors there are a little bit more tolerant in letting people study biochemistry and cellular biology without having organic. And I was kind of put in that category. So, and I'm grateful for that, because organic is kind of hard.
That must have been tough, because usually there's a sequence where you go inorganic chemistry, and then a small portion of that, of course, just the carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus is discussed in organic chemistry. And you go into the different, types of reactions and reaction mechanisms, but mainly you're just trying to learn the terminology, like what is an amino group or a carboxyl group, and then once you do that, then you can understand biochemistry. So you're jumping right into the biochemistry. That must have been challenging, having to learn the terms as well as all the principles and mechanisms. And
it was tough, and there's still some holes. And one of, I learned enough of the functional groups, and then my professor is really old school. He would have us just redraw all the molecules, and okay, he said, I want on the exam you're gonna recapitulate all 20 amino acids, and we do the diagrams. And then he said, okay, same for the nucleotides, and do diagrams. That was a good exercise. But then when he talked about nucleophilic attack, I said, yeah, I'm just gonna punt on these and just accept a doc grade. I still got A's in the class. I think in the second semester, our textbook was Leninger Principles, which I think is one of the more comprehensive. I did well in the second half, but I had to study hard, and I still need to actually go back and relearn it. And that's one reason I enjoy having these discussions. But there's one area that I'm just like, oh my goodness, I've seen this like 50 times, and I'm a little dyslexic. So there's the oxidation and reduction, and I keep getting them reversed. But Dr. Wile said he's looking at the oxidation states, and they're wrong if these are ancient. And if I'm not mistaken, the rate of oxidation is also governed by things like the Arrhenius equation. And I was like, okay, there should, in principle, then, if there is variation, because are you familiar with the work of Dr. Brian Thomas at the Institute of Creation Research?
Yeah, Rob Stadler introduced me to him recently. In fact, that reminds me, I need to give him a call. He wanted me to call him so we could talk about, he's doing some research studying collagen breakdown to verify or confirm or show that there's some problems with Mary Schweitzer's group with claiming that the iron free radical formation can cause cross-links sufficient enough for preservation. So they're doing some of those experiments right now in collagen decay rate determinations.
Because By the way, just an administrative thing. Michael Brusinak's here. I have not blocked you, Mike, on this channel. So if someone has blocked you, I didn't do it. So you're free to post as Michael Brusinak. He's one of our critics. He did try to teach me a little bit of organic chemistry. Sorry for that aside, Dr. Carter. And I talked to Dr. Thomas. I said there still seems to be some variation of the reaction rates based on the strata. And he said that definitely could be temperature. And so if we can see this across all of the biomolecules depending on strata, that would be a very interesting correlation. If the oxidation rates, the racemization rates, the collagen breakdown rates seem to have kind of the same effect based on the depth in strata. And we know some strata are thicker than others. And that would be a way to kind of test that and say, okay, this is definitely based on heat. It's not based on age. So again, I'm just throwing this out on the table for way in the future. And I was supposed 2.5 years ago, or maybe 2 years ago, I did have a conversation with Brian Thomas on this, and I got just pulled off on other projects.
Well, it does tie into
I probably have time this year to revisit it. That's why I was excited, because I started to access the oil cores, and they have the dates and they have the proportions of L and D amino acids. And I began to get excited because there was insufficient variation between the various strata. There were still some, and I'm just going to tally it, and maybe I'll just throw it up on Chem Archive or something. I said, we can't ignore this. Someone has to tally it. And what I did was I took R.H. Brown's reference list, and it's just a huge reference list. Maybe I could just show it briefly if I have it. Well, actually, while I look for it, I know I've gone way ahead of the readers here just because in my excitement to talk to someone about this who actually understands it and has worked with it.
That's why this is a nerd brainstorm. There we
go. It's a nerd brainstorm.
The nerdy details.
I'd like to invite people if they have some. I can't monitor the chat obviously completely, but if you all have a question, I will try to monitor. I'm definitely not going to be able to get to every question, but Dr. Carter, if you had some other comments while I try to get R.H. Brown's paper up.
Yeah, I did want to tie it into what we're talking about. So the main difference in the model, of course, is that you either have a geologic column that was laid sequentially, a couple million years of deposition, a couple million years. So obviously, the further you go down, the older layers, younger layers on top, whereas the flood model is that these layers were deposited somewhat at the same time, maybe a year, a couple of years. So the organisms that are buried in them, the testable hypothesis of the creationists is that you shouldn't see a pattern where you see a lot of degradation way down low and marginal degradation higher up. We would predict that you would see a somewhat random distribution of degradation rates by various mechanisms of analyzing that. So one of them would be, do you see more of a 50-50, closer to a 50-50 racemic mixture throughout the column, or do you see more racemization happening increase as you go down the column? Same thing with fatty acids. There are fatty acids found throughout the geologic column that still have their double bonds intact. They're unsaturated and polyunsaturated, monounsaturated fatty acids recovered from fossils throughout the geologic column. Well, if you've ever eaten a sunflower seed that has gone rancid, or smelled your olive oil cap that smells weird and tastes acrid, that's because of oxidation. Oxygen will break those double bonds, and they're very prone to reactivity. The double bonds are to these addition reactions. So it's not just oxygen. Water will break those double bonds and form alcohols. You can have halogenation, hydrohalogenation, but you certainly should not, even in a very hypoxic environment, expect to see double bonds there. I mean, even the radiation naturally occurring in the soil is going to start obliterating those bonds, and it doesn't follow the pattern that you would expect, where the further you go down, the less double bonds you see. It's just sort of random, really dependent on the burial conditions. And you could say the same thing with the length of proteins. The further you go down, the more time they've had to hydrolyze and break into smaller fragments. So you would expect shorter fragments of proteins the further down in the column, longer protein lengths, polypeptide lengths higher up in the column. And same with DNA, shorter fragments as you go down. DNA is even more fragile than proteins. And you could also do carbon-14 analysis on these samples, because carbon-14 there should not be any carbon-14 remaining in these organisms. After, say, like 100,000 years, you couldn't detect any carbon-14. But so far, in all the samples that have been analyzed, over 100 samples, carbon-14 is present. And so that's sort of a verification that either we've got a major problem with carbon-14 dating, and there's almost universal contamination. I mean, even the blanks they're using to calibrate the machines are showing up with carbon-14. So either we have to throw out all carbon-14 dates, or there's some unknown mechanism that explains this in situ production of carbon-14. I mean, the amount of radioactive material like uranium you would need in order to generate carbon-14 in place, in situ, would obliterate the molecules, and you'd have to have like 1,000 times as much. I don't remember the exact number, but you'd have to have significantly a lot more radioactive material in order to create carbon-14 to make it look like a contamination. And maybe if water trickled down fresh carbon-14 and introduced it, you can control for that. You can isolate it from whole tissues. And it's, as far as I know, that's still been quite the dilemma of explaining why carbon-14 is so prevalent in these tissues that are supposed to be totally dead of radioactive carbon. It's got too short of a half-life, 5,730 years, give or take 30 years. There shouldn't be a single atom of it left after like a theoretical age of 300,000 years, and yet you're finding it in coal, which is supposed to be 300 million years old.
Exactly. I mean, I have gotten some flack from my fellow young Earth creationists. I said there are problems in our young Earth model, but I wouldn't want to be defending the other side. I said maybe the fair thing is to say let's just admit that each model, as of right now, has its problems, but it can be resolved with future data points. And the data points, what I've seen over the last 20 years, is the data points have been more favorable to a young fossil record. At the time I was going through my kind of conversion to young Earth creationism, we didn't have Mary Schweitzer's stuff. And then that came in. And then now I'm hearing about, I just learned something about the fatty acid. By the way, I just learned something today. I didn't, is that why the olive oil tastes bad? I did not.
We are designed to not want to eat rancid oils because they're toxic. They increase, that lipid peroxidation can cause inflammation in your arteries and lead to heart disease. So there's a reason why it tastes bad. And you spit out that old sunflower seed that was sitting in a bag in your car for.
I'm going to be cleaning out the cupboards here in the pantries of, because I had these, I had some of these crackers and I couldn't believe how bad they tasted. I said I thought these would store away because I'm a bit of a prepper and I didn't know it. And I'm just like, this is just so horrible how it tastes.
Yeah, you need to have a lot of vitamin E or rosemary extract or something to act as an antioxidant. It's a lipid soluble antioxidant to protect those double bonds in the lipids, and even then, eventually those will get used up. When the grain is kept intact, it's got the husk and it's fairly well sealed. I understand they've even recovered some ancient grains from like Egyptian tombs and were able to sprout them, or maybe not Egyptians, but from a long time ago in these varieties that we know didn't have, and now they could recover them because they were so protected in that impervious husk. And once you ground it into flour and make processed food, now you've exposed it to oxygen and water and things that are going to accelerate the rancidification of those oils, as well as the other important molecules, so that they become they turn into something that's actually dangerous, harmful for your health.
Well,
but I like the point you're bringing up about, obviously both models, there's unanswered questions, and we're making testable predictions here that anybody can do if they have the money and the time and the interest to verify them. But what's disturbing is you only hear about the problems with evolution behind closed doors, where scientists will feel comfortable talking about it. But the way it's presented to the public, there's no disputation of the conclusions. It's, oh, this is how it is. And then you get the news to talk about it. And, well, this is just scientists have shown, or science confirms, and too often it just totally glosses over the number of problems that remain, or scientists from both sides of the arguments finding contradictory results, and that stuff doesn't get very well publicized. So I think that's why it's important for people like you and your channel to reveal what some of the struggle is about. It's a shame that this stuff doesn't get more attention, because people get the impression that it's almost unanimous that all scientists know that this is scientific fact and this is proven, which you can't do in science. Only in math can you really prove things. But it just doesn't get the same light of day exposure as the handful of creationist scientists that are doing work in the laboratory and proposing problems. That's this is from
right.
This is right the 5 miles from my house. One of my good friends just became the director there because the previous one retired. I think this is a 1985 paper. Yep.
Yes.
So he did it. They dedicated a whole origins issue to amino acid dating and the problems with it.
And this began to spark my interest. I went through this paper, and I want to again. He has a list of all I just wanted to mention, the Lord's helping us along, because it's the secular world that's doing all the heavy lifting. And there is a discussion. It's like, well, should creationists be investing in their own research? And I said, okay, well, we don't have the $40 billion a year budget that the NIH has, but the NIH they're doing research that's beyond our wildest dreams to show the complexity of life. And I said, okay, we don't have to do it. God's providing that for us. And then all this stuff that's being happening in paleochemistry, even though it's not as much as we'd like, they actually did a lot of it because there's interest in amino acid racemization as a dating tool, because it was cheaper than the accelerator mass spectrometry with C14. And they were thinking maybe this could even go farther than the carbon limit. And it ended up not being quite as accurate, but they still got a lot of data points. And I wanted to spend 2 weeks just going through all these papers and gathering the actual L and D amino acid ratios across the strata. If we could, God willing, someday someone is brave enough to start doing that for the other, like Mary Schweitzer's fossils, and that might be helpful. And so anyway, I'm just going to point the viewers to, this is the paper that inspired part of what I was doing. I'm going to put it in the chat.
And Sal, if you want copies of these papers, I have most of these. The paper I wrote only has, I think, like 56 references, but I have PDF copies of all of them. My paleomolecules paper is going to be much bigger. In my EndNote library, I'm already over 800 references, and I've only read through maybe 150 of them. So I still have a long way to go.
Oh
I'm
my
not going to
goodness,
use all of
yes,
them in the
yes.
paper, but it's a
Well,
daunting project. I've got papers going all the way back to the 1920s. You know, Mary Schweitzer wasn't the first one to discover soft tissues and
oh my goodness.
dinosaurs, but
Well, I know I'm where I understand where you're at, because these are interesting things, and we just don't have the time and availability to pursue it as much. But you know, again, I just keep seeing the Lord is providing. We have people like Mary Schweitzer, and God bless her. You know, I can, you know, I pray for her, and I think she's a sister in Christ, and she's gone through a lot of problems. But she, even though she's on the other side as far as the creation evolution controversy goes, she's actually done a lot of good work for our side without meaning to. So
I have to say, though, she gets really upset when we use her publications to support a young creation. She came and spoke at our university, I think at least twice, Loma University. But yeah, I know I'm praying too. I hope that sometimes you get so caught up looking at the trees that you don't stand back and see the beautiful forest for what the big picture is trying to express. And I think one of the neat thing about these proposals where we could do these various chemical tests and see if it follows the pattern that you would expect if long ages was true, or if the deposits were made rather contemporaneous. I mean, if people have the budget and they want to silence creation scientists, they're welcome to do these experiments. You know, these experiments are repeatable, and they if anyone could write a grant and do these types of experiments to see which data and results supports the best model.
and I just put Michael Brown's stuff on there, and I'm going to just share the screen, and maybe maybe we'll wrap up in 10-15 minutes, because I could see that we could be thinking and pondering this for days and weeks, and this is just a good introductory meeting. And then, you know, maybe through the emails we could exchange data. I have to get a lot more spooled up in organic chemistry, and then also just relearn biochemistry. I'm looking forward to this year because I'm going to be making YouTube videos to teach biochemistry and organic chemistry, partly because teaching is a great way of learning. And so the thing is when I feel just like when we were watching Rob Stadler's presentation, I said, oh my goodness, if creationists just learned a little bit more biochemistry, they would totally appreciate what Rob Stadler has to say by even more levels, because it was convincing even as he presented it. But because I've had a little bit more background than someone who's never been exposed to this, I'm just like, this guy is just so on the mark. I mean, I can't, it's hard to convey that. And it's like, if people have doubts about this, just learn more basic chemistry and you'll see it. And this is one example here is for the young fossil case. The more that we study the actual basic chemistry, the more convincing it is. And you gave me some data points I wasn't even aware of. You just mentioned all the stuff with the lipid chemistry. And so
most people don't know about that because those papers came from like the 1950s, and no one's really done much on it since. And they could easily, with even better equipment, take the lipids out of different organic remains from various layers of the column and categorize the types of lipids and see what percentage of them still have their double bonds intact and which ones have been chemically modified. And I'm surprised I haven't seen any more papers since then. But yeah, from all the samples they got, it was it didn't show a pattern in the column. It was just, so you had samples that were, supposedly tens or hundreds of millions of years old that still had double bonds in the fatty acids, and some of them higher up that they couldn't find hardly any double bonds still intact. And they analyzed quite a few samples, but obviously there's more work to be done. So there's a lot of fruitful research, bench work to do for these types of studies.
and the reason I'm kind of giggling a little bit is that what are they going to do? They're going to try to explain chemical kinetics for the nucleotides, and then chemical kinetics for the amino acids, and the chemical kinetics for the fatty acids, and come up with new theories with no justification experimentally or theoretically. And the weight of the evidence just keeps growing with every year, and I'm totally seeing it. And that's people say, why do you believe this? You don't have all the data points. I said the trend has been favorable on many scales in the last 20 years. And then the whole thing with genetic entropy and deterioration, when I was in a debate with Dr. Dan, and I asked him point blank, I said, do you think the human genome is improving? And he didn't give a straight answer. I'm like, you could say yes, no, or I don't know. And I said, what do you think about all the other geneticists who study this who don't think we're improving? He said, that's an argument from authority. I'm just like, okay, all right. You want to say that, but the responsible thing to say is, hey guys, the weight of the evidence is that maybe humanity's recent. I just can't run away from that. And so that's why I've been encouraged. So anyway, I'm just going to share this briefly with the readers here. And there's a graph here. And
I'm glad that website's still up. I saw this one 15 years ago or something. So.
I'm too. Maybe I'm going to try to save this because this is one of the most important.
Yeah, that graph.
Yes. And this is, let me see if I could, I'm going to try to see if I could bring this graph up. I have it somewhere here. And I redid it. And I've been just obsessing over that graph. And I do apologize. I have to try to reconstitute this graph because to understand it as is a little bit difficult, because it would have been nice if it were expressed in terms of just the L and D ratios, but then it does it in terms of racemization constant, which goes through, it's not as pure a number. But let me just graphically say this. If we had, if the fossil record were old, the data, okay, so these little dots here are the actual data points we got from the, like things like shells and coprolites, I guess, the dung and wood. The shells are kind of beautiful. They gave very nice graph. If the fossil record were old, and they only went up to 1 million years, unfortunately, I wish they had samples from like 400 million years. If we can get that, this will be really killer. If it were old, the rate constant would be relatively flat, give or take variance. And not only that, I would actually almost guess the variance would increase over time. But instead, we get this slanted graph, and I'm just like, oh my goodness, this is a systemic error. You shouldn't be seeing it just like this. And you should also start to see the error bars get kind of bigger. And I looked at that. I'm just like, my jaw dropped. And I want to recapitulate this graph. You would understand this graph if you went back, or you probably already understand it already. I need to rework it, and I've been meaning to do that. When I looked at this graph, it just, my eyes popped out. And so now what you're also telling me is we might have similar issues with lipid dating, the fatty acids and oxidation. And then now with Brian Thomas with the collagen breakdown, we'll just have all these chemical clocks, not to mention now the C14. And also because I studied a little bit of astrophysics, this whole thing with the faint Youngson paradox, I'm just like, I wouldn't want to be arguing on the other side. I mean, they have some good arguments on their side, obviously, but some of this basic stuff just is just too much for me to ignore. So anyway, if you had any closing thoughts, I've just been overwhelmed with some of this new data, and it's telling me all the stuff I need to learn over the next year to get more versant in this.
Yeah, I was going to try to share my screen, but it looks like I have to change some privileges on my computer that requires a reboot. So it doesn't look like it will work
Oh, wait.
I don't think it's showing right now.
Hang on.
Oh, there it is. Okay. Yeah, this is the equation they use to get that. So that constant, the K for constant, and that it should be, like you said, a flat line when you incorporate the concentrations of the amino acids here. And why isn't it a constant? There's something. It's interesting that they align along a linear relationship, but what is the mechanism that's doing that? And of course, one of the big problems is just the tremendous amount of variability and the things that can accelerate racemization. Just to give you an idea of how much temperature can affect things, just a 1 degree temperature change can cause about a 20% change in the racemization rate. So there's even one paper where dentists looked at, or forensic scientists looked at the wisdom teeth proteins. And, you get your wisdom teeth later in life, so they're obviously not as old as the other permanent teeth in your mouth. But as a person gets older, the racemization rate starts, because it's warmer in the back of the mouth by maybe 1 or 2 degrees different, the amino acids will start to flip and look older than the teeth really is. So it'll make the wisdom teeth look like they're older than the teeth in the front of the mouth, even though they started obviously growing later. So that just shows how temperature sensitive, how much temperature can accelerate the apparent age of proteins by their amino acid racemization. And of course, pH has a tremendous effect on racemization. I don't need to go into all the different factors and all the problems they've had where the expected age was nowhere near what the racemization age was. But the bottom line is we know of all sorts of ways that can make amino acids look older than they are. In other words, you get more of the L flipped to D, but we don't know any mechanisms that are going to reverse that except for enzymes. There are racemase enzymes that would flip the D back into L. And there's even some organisms that purposely introduce D amino acids to try to protect their cell membranes from enzymatic degradation because the enzymes won't recognize them. So a lot of the archaeobacteria, some of their amino acids, up to half of them in their cell wall will be the D isomer because they have racemase enzymes that purposely make it so that they can avoid degradation by enzymes. And even some toxins like cone shell toxin, funnel web spider venom, and platypus venom has some D amino acids that are purposely put in there. It's part of their, presumably part of their mechanism of wreaking havoc. But yeah, with time, temperature, pH, the presence of water, all of these things cause the L amino acids to racemize, but you're not going to get something that's going to really permanently preserve it in that configuration or reverse it. So we can use those facts to look at proteins throughout the fossil record and come to the conclusion that they cannot be millions of years old. And then you can corroborate that with carbon-14 data, which is more expensive. I think it's like $600 to send one of the samples. And I understand the rate group, radioisotopes and the age of the Earth, they sent their samples unlabeled to one of the top accelerator mass spectrometer labs in the world for carbon-14 dating, and they caught wind of it and they banned them from sending more samples.
Yeah, well, the thing that got me was when they were trying to make the blanks, not the rate group, but just the people trying to calibrate because they really wanted to have more business. They couldn't get the diamonds they couldn't find diamonds that didn't have C14 in them. And I'm just like, oh my goodness.
Again, they also use natural gas, like purified natural gas as a blank, and that was still having carbon-14 in it.
And I because I studied physics and I look into, actually I've shared this story. I was not doing so well in my graduate school solid state physics class, and I gambled. I said, I'm just going to do such an outrageous topic. I'll either flunk or he'll love it so much. It turned out my professor loved it. He said that was the best topic of my peers. And I looked at the electrical and chemical influences on radioactive transmutation. So even if radioactive decay rates are relatively constant over time, I say relatively, we can change nuclear structure. Electrical effects, and we're actually surprised even chemical effects can change nuclear structure. We've been able to affect nuclear transmutation. And I said, this has changed everything. This has changed everything because then it affects the daughter product ratios. I said, we now have a mechanism to explain maybe the daughter product ratios. And I got very, very excited. And so when I was looking at this whole thing with the diamonds, and people are saying contaminations, I said, forget it. Diamonds aren't going to be contaminated because they're so hard.
Yeah, it's pure carbon. So any carbon-14 in there is how is it going to get intruded into the diamond when it's such a solid crystalline structure of three-dimensional lattice of carbon? So how could modern carbon-14 penetrate through the diamonds? But yeah,
exactly. And I looked at it and I said, this may be suggestive of the mechanism of why there's still carbon-14 in there, is this whole thing with nuclear transmutation. There probably was something with the flood. If there was a big electrical component, because they had the piezoelectric effect, that they actually, during earthquakes, they see lightning coming out of the ground. There's a lot of electricity when there's geo, and it's like, oh my, this can explain, now that we've observed electrical influences on nuclear structure, there could be transmutation, and the transmutation can give all sorts of daughter products too. I said, it's a whole new ball game. What's helping us now is Mitsubishi Heavy Industries is investing a lot in low energy nuclear reactions because they're trying to make low temperature fusion devices. Everyone's interested in green energy, but even though they haven't been able to have like a positive net nuclear reaction where you have more energy coming out than you put in, what they have demonstrated is they've been able to do lots of nuclear transmutation with electricity. And that was
is that the Proton 21 labs?
Not just the Proton 21 lab. That was the first. And that was high energy. Mitsubishi is doing it at lower energy.
Wow.
And so I'm just like, okay, even creation stuff aside, again, God seems to be putting interest for the secular world to be doing our research for us. They're going to be throwing a lot of money at this just because of the green energy move. And I'm just like, okay, now we're going to get the research we really needed. So we really needed it, like with the ENCODE project and all the complexity. The biotech firms are just they're handing us the complexity argument on a silver platter. And now we're beginning to move forward on other fronts, not because of anything the creationists are doing. We just have to monitor what's happening. And it was kind of my full-time papers are out there, and just like I told Dr. Sanford, I can't even read them fast enough. There's so much happening. And that was just regarding the eukaryotic nucleus. I wasn't even talking about anything else.
Yeah, that should be our next topic. We can talk about
eukaryotic evolution.
Right. Man, I wish I could just do this full time. Like you said, you collect more papers faster than you can read them, because you look at the references of a paper and you're like, oh, I don't have that one, and then pretty soon you're like overwhelmed with papers to read. It's really a full-time job.
Before I say goodbye, there was one person in the chat. He said, Kane Wilson, he said, I believe that the Earth is probably about 4 billion years old, but that the radiometric dating is far off. This is primarily because of the faint young sun paradox. Or against such an idea. Why? I have my personal beliefs, and I think the best thing to do is just keep looking at the data points. I think the faint young sun paradox says the fossil. Let's just assume. I've often said, if I had to just have a model, not to express my personal beliefs, but just say one that I think, given the data we have, is at least halfway defensible. Just purely on scientific grounds, I'd say, okay, let's just assume the Earth is old, just for the sake of argument. Does that mean the fossil record is necessarily old? This would be like saying, okay, if the Earth is 4.5 billion years old, therefore the dog we find buried out somewhere in the field has to be that old. I said, no, you date the time of death. So all this chemical dating is showing the time of death could be relatively recent. The faint young sun paradox does pose a problem in that we would need global warming, and it had to be miraculously fine-tuned for the fossil record to exist. We can't run away from that. So again, evolutionary theory needs miracles to support it, which relates to next week's topic. If we assume that eukaryotes evolved from something like a prokaryote, I would argue that it would need miracles on the order of special creation to make it happen. So that'd probably be the topic of next week if you have time, maybe around the same time. Okay. Well, we've covered an awful lot in just an hour and 10 minutes.
Yeah, it's pretty heavy chemistry. I know I've been studying it and teaching it long enough that I've forgotten what it's like to not know it. And so I have to be careful because I throw out terms like a foreigner that suddenly goes into speaking their foreign language and you're like, wait, what? you lost me there. So I mean, this was a little bit of a more technical explanation, but hopefully, I guess if we could reiterate the gist of why we're talking about that, and then I wanted to end on the some of my two of my favorite quotes that deal with science and theology.
Well, definitely, I'm going to give you the last word with that. I just wanted to say that's why I titled this Nerd Brainstorm. I think there has to be somewhere on the net where they actually get things at the graduate level, because I know that there are biology students out there who are creationists or ID friendly, college, graduate school, even professors. And this channel is a little bit more organized to kind of encourage them, because they're outnumbered in school and all. So unlike other channels, this is actually a feature of this channel, is we have these conversations that people at that level of science training, they can relate to it. So with that, go ahead and I'll give you the final word. And I'd like to thank all the viewers who joined us today.
Yeah, I just wanted to tell the viewers, especially those that aren't scientists, that the more you learn about science, the more humbling it is. I mean, just when you think you've got something kind of figured out, you go deeper and you're like, wow, I'm only scratching the surface. And you realize that no one human being, even if they lived to be 1,000 and had a photographic memory, could even hold all of the information there is to know about some of the fields, like in biochemistry. I mean, you could spend your whole life studying just one pathway. So there is a tendency, when you look at a graph of like the level of education you have and whether you believe in God or not, you'll see that the more school you've had, the more likely you are to be an atheist or agnostic. And at some point, I think if you really dig into the details more, if you're at that point and you're like, yeah, it's embarrassing to pick the side of my upbringing of a creationist worldview, because I'm surrounded by very smart people in academia who think it's as ridiculous as, believing the moon is made out of cheese. But I want to encourage you that there are quite a lot of PhD level scientists, a lot of them even Nobel Prize winners. Most of them won't go public because they'll lose their jobs. This has happened time and time again. And even Discovery Channel helps defend some of these scientists that have been persecuted for just challenging evolution, not even presenting like a young Earth creation viewpoint, but just say, hey, we haven't solved this yet, or this is another big problem, or here's a huge gap that we have to tackle. And there is a lot of pressure. I do believe that, every one of us is biased. We all come in with what we have or expectations. That's why you have to be careful when you're doing experiments, that you use appropriate controls. And the ideal team would be a team that included both young Earth creationists and long age evolutionists, and you're looking over each other's shoulders, making sure no one's doing anything sneaky. I mean, from a creationist scientist standpoint, we're held to a high standard, right? It would be dishonest. We would be violating God's command to not lie if we were trying to fudge data. You know, certainly there's a lot of people that are ignorant about things, and they just, or their bias blinded them to certain results. But we try to have a high level of integrity, and the more you study science, eventually I think a lot of people get to the point where they start to get the bigger picture, and they go, aha, and it's really hard to change the idea is your worldview that you grew up with. We usually indoctrinated by our parents and then our teachers, and then you might get to the point where you say, well, what did my pastor know about science, or my mom or my dad? And clearly these professors have been studying science for a long time, and here's what they're concluding, so I should just side with them to avoid ridicule. And I had to go through that too. I grew up in the Christian faith, and at some point I had to know the answers. I had to say, why do I believe this stuff? I can't just say because that's what my parents said, or that's what my pastor says, and I wanted to know these things for myself. And most of my school was at secular universities, and I got to say, going through all of these science classes, that's where I found some of the best scientific arguments against long ages and evolution, and figured out these gaps for myself. But a lot of people don't do that. We're not really trained to critically think in school. We're rewarded for being able to regurgitate what the professor wants you to on an exam, and you get severely punished if you step out of line and question certain things that especially are sensitive because they affect the big questions in life, like where did we come from, why are we here, is there meaning in life? And, so that's I think that's one of the reasons why this topic brings out the best and worst in people, because if someone was just wrong about their data, you'd say, oh, looks like you didn't see this here, but you wouldn't see the kind of vitriolic animosity and just this pursuit of trying to attack each other's integrity and character and badmouth each other. And I see it on both sides too. I get sad when I see Christians who are supposed to be defending God's word and God's honor start defending their ego, because that's not why we're trying to do this. We should have pity and compassion on people that have come to conclusions based on misleading or incomplete evidence. And it's sad. You imagine from God's perspective, He's got His children, and some of His children might need a little more help than others. Anyone who's had kids knows that some of them might struggle with discipline more than the other. But the parents don't like to see one child demeaning, bullying, teasing, attacking physically or verbally the other child, even if the other child was misbehaving, because it hurts. It hurts God to see us attacking each other, his children, His creation. So we need to be careful about how we approach people. We need to be honest about what we know and what we don't know. Have curious minds, and I encourage you to never settle with a position, but to keep testing and keep probing and keep learning about it. Don't say, well, I want this to be true, so I'm going to find the evidence that supports it, and then, aha, now my mind is settled and no one's going to change it, because that's how you get stuck in dogma, and it's very difficult to change those paradigms. And that goes for both sides of the debate. But I've been collecting quotes from famous scientists that have to do with their position on God, and there's two of them that are very similar that I like to tell my students that people that are brilliant. Werner Heisenberg, the 1932 Nobel Prize winner in physics for quantum mechanics, said the first gulp from the glass of natural sciences will turn you into an atheist, but at the bottom of the glass, God is waiting for you. And then similar, Louis Pasteur said, a little science estranges men from God, but much science brings them back to God. Pasteur also said, the more I study nature, the more I stand amazed at the work of the Creator. So that's one of the things I love about science is, it helps us just peek into the mind of God and have this amazement. It's bewildering and complex, but just fascinating. And it actually brings me closer to seeing just the aesthetics and the beauty of the things he does, and that he's not just some mad scientist that is indifferent and doesn't care about us. And when you see the foresight and the planning that goes into making the universe work and having life work and be sustained, you start to see the picture of that God who is sorrowful when even a sparrow falls, or that knows the number of hairs on your head. He's that intimately involved in your life. And so as you're studying science, try to have an open mind about the possibilities of what these things mean. And it's not easy to change people's mind. It's not easy for you to change your own mind, but I just request that people do it with dignity and tact, and an understanding that everyone's coming from different areas. We all have different upbringings, different traumatic events that help influence our worldviews, and to just have compassion on others. We come at it from different angles, creationists and evolutionists. Creationists want people to, we're pushy for a different reason. We're not here to try to protect our egos. We're trying to save lives. So it's like if you're on the other side and you feel like you're being whipped and it's really annoying, we're like the people trying to whip the stubborn mules that are on an active volcano that's about to erupt. Or, when you see a total stranger in a crosswalk and they don't see the car coming, and yeah, we can be pushy sometimes, maybe even obnoxious, but we're doing so because we care. We're concerned, like, hey, you didn't see it, but that car was coming. And from the other person's perspective, like, why are you being so pushy? Why did you just push me? It just scraped my knees. And you're like, because I care, because I'm concerned, because there is a timeline here. There is a point where you may no longer have the opportunity to change your mind. If you're sitting on the fence and your time comes, maybe 50 years from now, maybe tomorrow, we don't know. And that's why there's this urgency and this pressing from the side of creationists. So try to understand where we're coming from and why we're so earnest and zealous about this. It's because we care. It's because we love even those of you that we've never met, that we want you to understand just how awesome God is, that he's not that scary God that is portrayed as genocidal and a control freak. And if we start from a reference point, we can't talk to the Bible about you if you don't believe the Bible is an inspired word of God. So we start with science. We try to meet on the same playing field. Okay, I've gone on enough on my soapbox, but
well, I want to thank you for, this has been one of the greatest sessions I've had. I love talking about science. And before I forget, do you ever get to see Chris Roop? He was Dr. Sanford's co-author of Contested Bones. He and I I still work for Dr. Sanford, but if you see him, I've actually never met Dr. Timothy Standish. He and I were at the same university, but it's 35,000 people there. We never met. So I was very flattered to hear that you'd work with
Chris. I haven't met, but Tim Standish and I have known each other, probably more than 15 years. He invited me to give a talk at a creation conference that was in Salt Lake City many years ago, but he and I still keep in contact. In fact, he updates me on some of the latest publications on ancient biomolecules, sends me emails of the latest papers that I'm adding to my list. Hopefully I can get through those 800 or so papers and get this thing published finally, because I've been working on and off since 2005 on it. I just was too busy the last 10 years starting all these new courses, but now things have settled down, I'm able to pick it up again and tackle those papers, write a very comprehensive review on this subject.
I look forward to working with you this year for whatever.
Likewise, yeah.
Collaborate. I'm going to be freer this year, as my contract with Dr. Sanford it's not over, but it's winding down, and
That's what I heard. Yeah, he's retiring or getting ready to, or
he's technically retired, but I a lot of it's been saying, Doc, can you just slow down a little bit? We'd like you to enjoy life. And he's like the hardest working person I know. And there he was.
I met him once. He's been to Loma Linda to speak as well a couple times, and I got to talk to him. He's a really nice guy.
Yeah. And he probably came out that he may have talked about the nylon eating bacteria. That was the project we were working on.
I remember that. Nylonase is just a amidase, the same kind of enzymes that break peptide bonds. They're ubiquitous, as you know. That enzyme did not evolve after the advent of nylon. It was already there to begin with.
Yep. So all this to say is that I may have free time, and I told Dr. Sanford I want to devote this year to developing my educational business, even if I may not make any profit from it. I'm committed to relearning all this, and one way to relearn it is to teach it, and then if I can help some of the biology students or any other students just get supplemental stuff, I'm grateful, and they could see it from a perspective that's friendly to creation. So I'm really excited. I feel it was very provident we ran into each other, because I'm thrilled. And I continue to be amazed how many biochemists there are that are friendly to ID. They're not
you'll probably find more ID friendly scientists in biochemistry than just about any field, I think, at least in my experience. You just reach this point where you have this aha moment. You start looking at one of these complex pathways, and you're like, that is just fantastically beautiful and complicated, and shows so much foresight. And then you start to think about all the chicken and egg scenarios, these circular causalities, and you're like, okay, which came first, the ligand or the receptor, the enzyme or the substrate or the inhibitor for that enzyme? There's just countless of examples of it, and if you're open enough to see that possibility, it hits you like a ton of bricks. You're like, not only do we have a creator, but he is just far beyond the genius of any human being, and it's exciting. It's like getting to have a peek at the laboratory of God, as this sort of apprentice that gets little snippets of how it's done, understanding how life works down at the molecular level. It's overwhelming and exciting at the same time. But I look forward to doing some collaborations. I know we talked about possibly making an e-textbook that addresses some of these issues from a more critical evaluation, looking at it with an open mind, and not just criticizing evolution, but also presenting some of the scientific evidence that supports the Bible's testable claims. If we can find a way to do it full time, I'd love to. I've been teaching, but I've got a hungry mind, and I get kind of bored explaining the same thing over and over. And I'm at that point now where I've already created 15 different courses, and now I'm repeating myself, and I want to do other things. So if I could find out a way to sustain myself doing this full time, I would love to.
Well, maybe we could just, for now, it might be just a trickle, and today was a start, and maybe next week we'll talk about the eukaryotic evolution, and we might be able to get Dr. Tan. She actually, before the Stairway to Life, she's working on, it was actually the eukaryote prokaryote divide.
If she should come next week, I'd like to meet her. I already read her and Dr. Sadler's book a couple of weeks ago, but I have not met her in person yet.
Oh my goodness, her one with Dr. Tompkins on eukaryote, I crawled through that. That was just like the most miserably difficult paper I've ever read. But I said I'm going to read it. So with that suggestion, I'm gonna invite her next week, and we could talk about eukaryote prokaryote divide. And I had some things with the localization, and I expect we could actually have several conversations on this because there are all these systems in eukaryotes, like the nucleosome system, and then all the intracellular transport.
Yeah, how do you get mitochondrial proteins destined for the mitochondrial matrix that are encoded by the nuclear genome to transport across both sets of those membranes? It's pretty complex, fascinating process.
I'm going to specifically invite her, and she's like, she might be able to come, and we can also, it'll give it a chance for her to also promote her work, her Stairway to Life, and then also some of her work on eukaryote. I might actually ask her, I said, can we maybe even consider a joint article among all of us together, just as an educational one.
Yeah, as you know, I meet with
more for PhDs. I need something a little bit lower than that.
Yeah, Rob Stadler and I and a couple of other chemists and biochemists, and one of my friends who's a geologist, we meet every week and are working on making these videos for Origin of Life. So Rob was already talking about, we might have enough stuff here for a sequel or another Stairway to Life scenario where we cover some of the things that haven't been discussed yet, because there's so many more steps in that Stairway to Life that weren't even discussed yet. And
wow, this is exciting. Well, it's always good to end when we want to still keep talking, because it's bad when we're so sick of it of each other. We want to just end it, but
not at all. I can do this until people will get so bored that they quit. So maybe it's a good time to do that. So
yes,
I got to eat dinner anyways, but I'm just trying to scan through the comments to see if there was any questions.
They were asking if you had a channel. They were talking about if you have a channel.
Not yet. I am eventually going to I keep getting so busy, but I want to make a video going into some of the chemistry that challenges abiogenesis that hasn't been discussed yet, and it's technical. So I'm going to try to pre-record it using some models and animations and stuff to try to explain it so that non-chemists can understand it. And then I will have Standing for Truth show that on his channel and have a live Q&A afterward. And then eventually, when I finish this ancient biomolecules paper, I will do another video on that as well. So in the meantime, usually the weekends, I can just chime in here and there on other people's channels, and then eventually I'll get enough content to maybe start my own channel. But
well, we would be always honored here, and this is definitely a scholarly channel. So I'm trying to especially appeal to the science students out there. They would be very eager to hear from you. So I guess this is the conclusion of today's segment, and Lord willing, we'll meet again about the same time next week. So I'd like to thank all the viewers, and I'd especially want to thank Dr. James Carter for joining us this evening. So take care.
My pleasure. Really enjoyed it. Thanks, Sal.